Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Katherine Freese. She's a professor of physics at the University of Texas at Austin, where she holds the Jeff and Gail Kodosky Endowed Chair in Physics. She is known for her work in theoretical cosmology at the interface of particle physics and astrophysics. And today we're going to talk about her book, The Cosmic Cocktail, Three Parts Dark Matter. So, Dr. Freese, welcome to the show. It's a pleasure to have you on.
Ricardo, thank you so much for having me.
Great. So, let me first ask you, at a certain point in the book, you mentioned that the universe is composed of 5% ordinary matter, 26% dark matter, and 60% dark energy. I mean, I would like to ask you, where exactly do these percentages come from, and are they definitive or not?
This is a compendium of work that took place over the last 50 years. So there are many, many pieces of observational evidence for each of these numbers, and we are quite sure they are correct, actually. So I don't even know where to begin just talking about this, but one important piece of data comes from the cosmic microwave background, which we also abbreviate as the CMB. And this is the leftover light from the early universe, from the very hot early universe. And what we see is light that comes to us from the last time that these particles of light interacted with each other. So that was very, very early in the universe, and they come straight directly to us, and they're microwaves. So we see that as a microwave background. And from the studies of this light, we learn about these different components of the universe. This is one of the major tools that we use.
Right. So, talking specifically about dark matter and dark energy, when did people get the first clues that things like these might exist?
Yeah, that's actually the dark matter problem predates these measurements of the cosmic microwave background. Actually, this is a 90-year-old problem. It is one of the longest unsolved problems in all of physics and one of the most important. This dates back to the 1930s. So there were scientists in Sweden, Knut Lundmark, and then in the United States, a Swiss scientist, Fritz Zwicky, who were the first ones to talk about the idea that dark matter has to be there in structures. So, for example, Fritz Zwicky was looking at a cluster of galaxies, and this is a cluster that contains hundreds of galaxies. And what he was looking at, he saw, okay, if this is the center of the cluster, he saw things moving around the center. He saw these are galaxies, and if you know how much mass is in here, how many other galaxies there are, that should determine how fast these guys move. But they're moving way too fast. They were whizzing around. So he says, oh my gosh, there must be something else, some additional matter that's providing this gravitational pull that's speeding up these galaxies going around the middle. And he called it dunkle Materie. He was Swiss, so this is the German for dark matter. And people didn't really know what to think for a very long time. But there were. Can I tell a story about him, because he was quite a character?
Of course.
So he was, in his book, he called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. So he was kind of a crazy guy. So he made these measurements in the mountains in Los Angeles above Caltech, and they're actually quite high, these mountains. It's the same mountains, same vertical drop as the Alps, it turns out, and their telescopes were at the top, still are. It's for of historical interest at this point. And he decided to build a ski ramp up there for the, I don't know, 3 days a year that it snows. So he was a character. But anyway, so that was in the 1930s, and then of course there were other people who made measurements that complemented his work, and there was a big discussion and debate, is it true, da-da-da-da. But then it was really in the 1980s, the work of Vera Rubin, who completely, she nailed it. She really proved that every single galaxy she looked at had evidence of dark matter. And I don't know if I should continue talking about what she saw there, or...
Yeah, please go on for a little bit more, yeah.
Well, she was looking at Well, she proved that every single galaxy has dark matter inside it. And it was the same type of work I've described. It's called rotation curves. And so what you do is you measure, again, this time around the center of the galaxy, how fast are stars moving, or other objects. Or the stars are moving around the center of the galaxy, and again, they're moving too fast. You can't explain it in terms of the other stars. So again, there has to be additional material in there, the dark matter, that's speeding up these orbits, these rotations of objects around the center of the galaxy. And every single galaxy appears to have this rapidly moving stuff. And so then apparently every single galaxy has a lot of dark matter in it, including our Milky Way.
And do we know anything about the particles that are part of dark matter?
Well, at first people tried all kinds of things. What could the dark matter be made of? So the first thing to try was rocks or dust or snowballs of hydrogen or various things. But they would have given off various observational things that we would have seen. So they were ruled out pretty quickly. But then people still thought, well, okay, so it's not bright stars, but maybe there's just a lot of faint stars or even substellar objects that don't give off light, but they're sort of more like planets. And so these things, these light things, they were called machos, which stands for massive compact halo objects. What a name. And so I was one of the people who showed it can't be machos because, again, with some of the more recent telescopes like Hubble Space Telescope, which has better sensitivity, you would have been able to see faint stars. And then with other types of data, you could look at these sort of planetary types of objects and see how many of those there should have been as well, and it doesn't solve the problem. And so machos don't work, and so then the people start thinking, okay, I guess, well, what else could it be? And there was a debate. I like to tell this story because on the one side were the machos, on the other side were the WIMPs. The WIMPs are the weakly interacting massive particles. But even before we started talking about WIMPs, people tried. So yeah, the idea that instead of rocks or dust or macroscopic objects, it could be a particle. And that seems very logical because, look, the fundamental objects of our standard stuff, that's particles, neutrons, protons, these are particles. So maybe there's just some new kind of particle that doesn't interact very frequently, so we don't see it very often. And, well, there's one that everybody knew about, and that's neutrinos, which have been known, again, also for a very long time. It would be so lovely if a particle you knew about could explain the dark matter. Now, sadly, that did not work. And the reason for that, already known in the 1980s, was because neutrinos are very, very light. And so they would move really rapidly out of galaxies, and they would pull the ordinary matter also out of galaxies, and they would screw up. We wouldn't have galaxies yet. So neutrinos can't be the dark matter. And at this point, we actually really are learning about their masses from various experiments, including cosmology is a very important tool for learning about the mass of neutrinos, but they're really, really very, very light. And so they only constitute 0.5% of the universe. We know that now. Mm-hmm. Okay, so it's not neutrinos, it's not machos. So people are trying all kinds of different new ideas, and the two with the best motivation would be axions and WIMPs. Where again, so let me tell you about WIMPs. Mm-hmm. So WIMPs, that stands for weakly interacting massive particles. So the name tells you a lot, because let's talk about the four forces of nature. So that's what the particles in the universe could participate in any of these four types of forces. And well, the one is gravity. So yes, dark matter feels gravity. The definition of matter is that it feels gravity. Okay, so what else could it be? Well, electromagnetism? No, because that would mean that then the particles would give off light, which they don't. So not electromagnetism. What about strong interactions, which hold your nuclei together? And the answer again is no. That would be, we would feel it if we were hit by strongly interacting particles. That would hurt. So of the four remaining forces, the only one left then would be the weak force, which is responsible for some types of radioactivity. And so let's imagine that there is a particle that weighs, somewhere around the same as a proton, or 10 times as much, or not too far different from a proton. or 100 times as much. And then you ask, okay, how many of these would there be? How would they behave, and so on? Well, in the early universe, there were all kinds of particles, and it was very, very hot, very, very dense. That's what we mean with the hot Big Bang, that the universe, it didn't start from a point, by the way. It started out probably infinite, and it just kept, but it was very, very hot, very, very dense. All the particles smashing into each other all the time. And then as time goes on, the particles move apart, the universe cools. Do we know why the universe is expanding? No, actually we don't, but it is. So what that means is if you go back in the early universe, we can calculate at the very high temperatures how many there were of every type of particle, how they're interacting, and that includes the WIMPs. How many were there? How were they interacting with this weak force? And that means we can also ask how many are left today. So if you do this calculation, and assuming that they were around, and in fact, WIMPs are their own antimatter, that means when they hit each other, they annihilate, they turn into something else. Annihilation doesn't mean disappearing, it means turning, well, the WIMPs actually themselves disappear, but they turn into some other particles. And so they would annihilate until the universe became spread out enough that they didn't hit each other anymore, and there'd be a certain number left. And when you do that calculation, assuming that the weak force governed that annihilation, then you end up with the right abundance today to explain the dark matter. So people thought, wow, isn't that a coincidence? Such a coincidence, they call it the WIMP miracle. So there seems to be a reason why, there's a reason why WIMPs are really good candidates, because weak interaction is the only remaining force that makes any sense for particles to have. And lo and behold, you get the right number of WIMPs. And so let's talk about WIMPs today. Well, if this hypothesis is correct, it turns out that there would be 1 billion going through your body every second. But you're not, again, they're not strongly interacting, so you don't notice. They're not electromagnetically interacting either. So but every now and then, about once a month, one of them would hit a nucleus in your body, and I don't think it's killing you. So that's exactly the problem. They're weakly interacting, which makes it reasonable that they could be there, but makes them hard to detect. So that's another story. How are you going to try to detect these particles? So I don't know if you want me to talk to you about the other types of dark matter candidates, or how we would detect WIMPs, or where should I go from here?
Well, I mean, perhaps tell us first if we should expect for any of these particles to interact with in any way with ordinary matter, and if not, how would we detect them?
Well, the worst nightmare is that there's some kind of particle that only interacts with our matter gravitationally, in which case I don't know how the hell we're ever going to figure out what it is. But for the case of the WIMPs, yes, they would interact with ordinary matter. Very, very weak interactions means that it doesn't happen very often, it doesn't deposit much energy, but yes, WIMPs definitely interact with ordinary matter. So as I said, in your body, they would interact about once a month with one of the nuclei in a human body. So they do that. And so what we have to do is build detectors that are sensitive to these very rare low energy interactions. And actually that's where my work comes in, because in the I don't know, I'm going to date myself, but in the 1980s, we wrote some of the first papers. I did the calculations of WIMPs hitting, or exactly the answer to your question, I did these calculations. We used Feynman diagrams, which people often have heard of, and we're trying to calculate how many of these interactions there would be, and what would happen if you did hit some nucleus. And so, because your detector, after all, is going to be made of some kind of ordinary matter, and so I did these calculations, and then I worked with my friend David Spergel, and he put in the astrophysics of how many particles are there inside our galaxy, because the galaxy is mostly made of dark matter. So if you put these pieces together, then you can also compute, and our third collaborator, Andre Druckier. So we put together, well, then what would you expect to see if you build a detector? That's a consequence of putting all these pieces together. And what we realized is, well, so if you take a detector made of some kind of material, and you put it, you have to go a kilometer underground, because otherwise you're going to be swamped with other particles. Cosmic rays are particles that are flying throughout the galaxy, and they actually do hurt us as humans because they have electromagnetic interactions, and so which is why when you go in an airplane, the farther up you go in the atmosphere, the less protection you have against the cosmic rays. The atmosphere protects us down here. But if you live higher up, like the city in the United States, the city of Denver, you're already getting quite a bit more cosmic rays. Or you go skiing, you're going to get even more as you go far higher up. And on airplanes, if you fly around too much, you can get quite a lot of cosmic rays. And so therefore you have to put, the farther underground you go, they can't get through the Earth. So you build a detector that's underground. And these detectors are sitting there waiting for, not for the cosmic rays don't get there, but the WIMPs do because they're so weakly interacting. And then you, with your detector down there, if the WIMP comes along, hits your detector, scatters off of it, and deposits a little energy, and we computed here's how often that would happen, what energies you have to look for. So people started building detectors, and it's a worldwide effort at this point. And it's a complicated story. So I don't know if I should continue in this vein, but I feel like in a way I want to describe to you the Milky Way, where these particles are sitting. Should I go back and do that, or should I continue?
Yes, please go in that direction. Yes.
I think I should. I think I should give you the big picture of why dark matter matters. Okay, so let's talk about our galaxy, the Milky Way. And so this is interesting because at the center of every galaxy, including ours, there is a supermassive black hole. And that is, so in our galaxy, this is a black hole that weighs 4 million times as much as the sun. And in 2020, that's what the Nobel Prize in Physics was given for the discovery of this supermassive black hole, to Andrea Getz and Reinhard Genzel. Well, they got half the prize, and the theorists got the other half of the prize. But they and the way they found it is because you see things moving around, and they're moving again from their motions. You can determine there's got to be a big fat mass in there, and so they were able to prove there's this giant galaxy in there. But then people get confused. They think, well, why isn't that the dark matter? And the answer is that this is only a millionth of if you add up all the supermassive black holes in all the universe, it's only a millionth of the total content of the universe. So although it sounds like a big number, but it really isn't in the grand scheme of things. But anyway, so we have this central giant black hole in our galaxy, and then as you move away from the center of the galaxy, you can imagine it's like a pinwheel, a set of arms that in the form of different spirals. And it's along these arms that the stars are sitting. And for example, our sun is along one of these arms. All the other stars are too, pretty much. So if you then take this thing that looks like a pinwheel and you just place it on its side, okay, that's where the stars are. And when you look out into the sky, most of the stars you're seeing, that's where they are. The thing that people call the Milky Way, it's this flat piece it's the disk of the galaxy, but that is very tiny compared to the giant spherical stuff that is much, much larger in extent. So you have this tiny little spherical flat region, and then there's all this other stuff, and that's made of dark matter. So dark matter really is the predominant. It's what the galaxy really is made of on the whole, other than this small bit of stars. I mean, yeah, stars are only maybe 1/100th of the total content of the universe. They're really, not important in the grand scheme of things. To us, they're important. We want to live on one. But that's kind of the picture of what galaxies look like. So the dark matter plays a really predominant role in the existence, formation, today's galaxies. So dark matter is very important stuff. It matters.
But are there any good hypotheses to explain how dark matter might have come to be?
Well, if you want to go back in the early universe and you ask, well, how did quarks come to be? So we don't really, the beginnings of the universe, we're still not sure. So what we're imagining is at the beginning, from the point where we are able to discuss it, which is the definition of the Big Bang, just means that's where our discussion begins, frankly. Okay, There was no explosion or anything like that. But anyway, so at this very early stage, there were particles, there were quarks that make up protons and ordinary, all this stuff, the standard model of particle physics, the ordinary stuff that is completely understood at this point. All those particles were around, and the dark matter particles, if we're right, they would have been around. Everything would have just been there from the beginning. Okay, so the creation of the universe is the creation of the dark matter. That's the same question as the creation of the ordinary matter, so we don't have the answer. The reason that we don't is because, well, I talked about the expanding universe. Now let's go back in time. Let's contract, getting closer, everything getting closer and closer together. So everything in the room I'm sitting in, which is, by the way, my kitchen, all of that will, of course, go to a point. Okay, so the Earth, yeah, that will go to a point. But what about things that are out at infinity? Well, they're going to get closer together, but you know what? There will still be something at infinity. So the Big Bang was not a point in space. For us, it was really a point in, oh, whoops, I forgot to turn my phone off. My apologies.
No problem.
Okay. Anyway, so the Big Bang was not a point in space. It was a point in time. And what happens when you pack everything too close together is that our laws of physics fail. We just don't know how to write down the mathematics anymore once you get to a too high a density. And the reason is that we don't have a theory that incorporates quantum mechanics together with gravity. That's known as a theory of quantum gravity, and that's an unsolved problem. So if you want to go farther back in time, you have to solve quantum gravity. So there are attempts to do that, and the most famous one is string theory. So thousands of physicists are working on the idea that particles are not fundamental, that strings are fundamental. And I literally mean string-like objects, okay? And it's like the string of a guitar, and when the string wiggles, that defines a particle. Okay, so that's a weird idea. Or it could be a circular string also, and the wiggles of circular strings are particles that would be responsible for gravity. So that's the idea. Different types of strings produce different kinds of particles, and that could also explain gravity. So that's a possibility, but unfortunately, there aren't any predictions from string theory, so we don't know if it's right or not. And this question of how did the universe begin? We have to get back to this question of understanding quantum gravity.
So another question: what are the kinds of astronomical phenomena that, if we had a better or a complete understanding of what dark matter is and how it works, we would be able to answer?
So one of the reasons I mentioned at the beginning, there's a million pieces of observational evidence for the existence of dark matter, for example. Okay, and so one of them, this is pretty interesting, is that human beings would not exist if dark matter hadn't been there early in the universe, because it was the dark matter that formed the galaxies. So ordinary matter could not have, because ordinary matter was interacting with photons or particles of light. So just like neutrinos, the photons, because they're massless, they go zoop, they go out of galaxies, and so pretty much in the early universe, the photons were scattering with electrons. Okay, and so back when the universe was made of a plasma, which means free electrons and free ions, and then the photons moving out would pull the ordinary matter out as well. But because dark matter doesn't interact with light, it doesn't have electromagnetic interactions, it doesn't care what those photons are doing. So even though photons and ordinary matter are moving, woohoo, the dark matter can clump, it can collapse, it can start making interesting objects very early on. And so that's a really necessary ingredient, because if you want a galaxy, you need to clump stuff, and so the dark matter does that first. And then later on, the ordinary matter falls in along with the dark matter. And so understanding the formation of structures like galaxies and clusters and all of that requires us to understand the nature of the dark matter. So another way to look at this question is not necessarily what kind of particle is the dark matter, but what type of dark matter it is from the point of view of its behavior in terms of structure formation and so on. And so one of these issues is a question: is it cold dark matter? Is it hot dark matter? Is it self-interacting dark matter? And the two examples I gave already, the WIMPs and the axions, they're both cold dark matter. And what that means is that these particles are moving very slowly, non-relativistically, much, much slower than the speed of light. And that is kind of the paradigm. That's what people now are assuming is correct, okay? So it's called this picture of the entire universe of the 5% ordinary matter, 25% dark matter, 70% dark energy. That this standard cosmological model now is called lambda CDM. And the lambda stands for what's responsible for the dark energy, which we'll talk about later, I think. And the CDM stands for cold dark matter. So that's the standard cosmological model at this point, that you would have slowly moving particles that would clump together to make galaxies. And everybody thought, okay, that's a solved problem. That's why it's the standard model. But it really isn't, because there are some puzzles, some observations that don't necessarily match cold dark matter very well, and or do they or don't they? There's a lot of argument on the observations. So, for example, if cold dark matter is right, then at the centers of galaxies, as you move to the center, there should be more and more and more and more dark matter. So I'm moving the way my finger is going. I'm moving to the center of the galaxy, and the number of dark matter particles is going up, 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 up. So that was the prediction because people make cosmological simulations they simulate galaxy formation on the computer, and this is what they find, that the centers of galaxies should have a lot of dark matter. And now people argue about the observations. It looks like in some cases that is just simply untrue, that the dark matter at the center seems to flatten off. There's not more and more and more at the center. This is called the cusp core problem. Cusp meaning keeps going up, core means flattening out. And there are several solutions if these observations hold up. How could this be? Well, one possibility is that cold dark matter is correct, but later on there were stars, and stars made supernovae, and they pushed the dark matter around, and that's why they got rid of some of that central dark matter. That's one possibility. I like that possibility myself, to be honest. The other possibility, though, is that it's not cold dark matter. It's something like self-interacting dark matter. And this would be dark matter that, well, the WIMPs had annihilated among themselves, but imagine there's an annihilation that's even much stronger, okay? So that would explain why at the centers they would annihilate away, you'd have less. So there's a lot of interest in trying to understand, is it cold dark matter, self-interacting dark matter? Now, hot dark matter doesn't work, because that would be neutrinos, would have been hard dark matter, and that stuff means it's moving relativistically, and it would move out and ruin galaxy formation. So we know it's not hot dark matter, but it could be warm. It could be all kinds of different possibilities. And if you understand the nature of dark matter, then that'll restrict you to different classes of possibilities for the particles.
So let's now get into dark energy. What is it?
Everywhere. Yeah, okay, this is a really, really strange thing. So I've already told you that I'm pretty sure everybody believes in dark matter at this point, okay? Mm-hmm. But dark energy, oof, so on the observational side, we see what dark matter is doing to things. You can see it pulling things, it's there, okay? But on the dark energy side, even the observations are confusing, and dark matter also the theory. We have some very good candidates. But the dark energy theory, we really don't. We really don't understand much. So the contrast between dark matter and dark energy is the following. I think I mentioned earlier that anything that the word matter means is gravitationally attractive, which is why dark matter makes galaxies. But dark energy has the opposite behavior. It's some kind of repulsive behavior. The universe, as of the recent past, instead of just expanding, has started to accelerate. And that's really weird. So the expansion is accelerating, and that is the opposite of what gravitational attraction would do. That's the opposite of matter. So these two things, the only thing they have in common is the name dark. They don't give off light, okay? But ordinary matter and energy can convert into each other, but dark matter and dark energy cannot. They're just too different. So the way this was discovered originally was by looking at distant supernovae. So what these are they're stars that at the end of their stellar lifetimes, they have to be much heavier than the sun. But you take heavy stars and you wait a while until they're running out of right now the sun has hydrogen that's burning to helium. That's what fusion that lights up our sun. But if you have heavier stars, that whole process happens much more quickly. It doesn't last very long. And then these stars blow up. And in the process of blowing up, there's one particular type of supernova blowing up that we understand very well, and it's called a type 1a supernova, and we really understand how bright these things are. Okay, so that means even though you see them way back in the distant past, you really do understand them. It's dangerous if you compare today's galaxies versus early galaxies. Well, they can be quite different. So assuming you know what's going on is a dangerous game. But with these particular type 1a supernovae, we do understand them. So people looked at these distant supernovae and wait a minute, something's wrong. If we know what their distance is, then you should know how. Then they should have had a certain brightness, and they don't. They're dimmer than they should be. And so the interpretation that people came to quickly as well, that's because the universe is accelerating, so we're misreading the situation. So the dimness is due to they're accelerating away from us. That makes them look less bright than they otherwise would. Well, when I first heard this, I thought, oh, come on. There's got to be many explanations for this. And people did try a lot of things, dust in front that's obscuring the light or whatever, many different things people tried. But the same evidence is like a puzzle piece, this jigsaw puzzle with these three parts of the universe. The same evidence is there in all kinds of data at this point. So the cosmic microwave background that I started mentioning at the very beginning, the leftover light from the Big Bang, it has peaks in it. And if you look at and this is not peaks. Well, if you look at the microwave background in the sky, on the whole, on the average, it's all the same temperature. It's a microwave temperature, but certain spots are a little hotter than the average, and certain spots are cooler than average. And it's the size of these hot and cool spots that give you this ridiculous amount of information about the universe. So it's a little tricky to explain it, but so based on that data of where the hot and cold spots are, believe it or not, you can extrapolate very, very, very good information about how much matter there is, how much and how much dark energy there is. And so you see it not only in the supernova, but also in the cosmic microwave background. And then also it turns out the numbers of clusters of galaxies early in the universe depends on the amount of dark energy. And so you look at all these different pieces of evidence and they all cross at the same point. There has to be dark energy there. So I didn't want to believe it. Nobody wanted to believe it. It's just so weird because it doesn't make any sense theoretically, okay? It's just really weird. So in order to try to explain it theoretically, that takes us back to Einstein in 1915. All of cosmology started with Albert Einstein in 1915. All of it. You take his equations, people took the equations of general relativity, and then they applied them to a universe as a whole, and they realized, okay, so if in the universe, so here's how you do that. What are the equations for the universe as a whole? So everything I've been talking about, the evolution of the universe, is Einstein's equations as applied to our universe. So Einstein originally, in writing down general relativity equations, people didn't know, was the universe contracting or expanding or static, and he wanted it to be static. So it's before we knew. So he added this extra term called the cosmological constant that he would balance off against some other terms, and so they would equal zero, and then the universe wouldn't expand or contract, it would just stay the same always, and he liked that. But so that was 1915, the theory. 1929, Edwin Hubble looked at the sky and saw galaxies, looked at distant galaxies. First, he proved that distant galaxies exist because people didn't know that. They thought everything out there is in the Milky Way, and it's not true. He proved there are distant galaxies, and then he also proved they're expanding away from us. Mm-hmm. So, well, that means so this extra term that Einstein added is called the cosmological constant, so it lost favor. It was gone for a while. However, it's back. the equations are a little different. Instead of balancing off the cosmological constant, though, that other term that balanced it off is gone, but the cosmological constant would cause an accelerated expansion. So now that thing that Einstein called his biggest blunder is back, and people think that's probably the best explanation we have for what we're seeing as dark energy. But the reason it's so weird is that if there is, so you can also compute so what is the cosmological constant? It's a vacuum energy. What does that mean? That means everywhere in space, there are particles that, in this room, this is a fact, there are particles that pop into and out of existence. They only last 10 to the minus 43 seconds, okay? So you get a pair of electrons and their antiparticles, electrons and positrons, they come into existence, and then boop, they're gone again. And that's what we mean by when we say the vacuum. And it is, you can measure it, believe it or not. You can put two plates, okay, conducting plates, and then they're actually drawn together by this energy in between. So people have made that measurement. So it's real. And so however, if you do the mathematics for all the particles in the universe, you add up all the contributions, and what would you get for this number? It's wrong by 10 to the 122. In other words, 10 with 1, so with 122 zeros after it. That's how wrong this number is. It should be that much bigger than the vacuum that we observe so the dark energy it could very well be a vacuum, but the number, it's theoretically speaking, it's a disaster. Our calculations are wrong. It should be that much bigger than what we're calculating. So that's called the cosmological constant problem, and many of the most famous physicists in the world call it the biggest problem in all of fundamental physics. Other than, of course, figuring out what the dark matter is. That's another big one. Anyway, but this is a theoretical problem, purely theoretical problem that is really puzzles people like crazy. So then people at least thought, well, there's got to be some mechanism to drive it to zero. Well, wrong, because we do have a dark energy, and so it's not just zero, but it's a tiny number, and a tiny number that became important right around the time the galaxies became important. So human existence coincides with when this cosmological constant starts playing a role. The acceleration only kicked in fairly recently. What the heck? So it's a timing problem as well as a numerical problem. So the whole thing's just weird. So in the back of our heads, we do have another thought. We do know that ordinary matter and dark matter exist, okay? But what if somehow that's all there is? But what we've gotten wrong are Einstein's equations. In other words, Einstein's equations, well, they're not wrong. They certainly explain a lot of things, but they're incomplete. So I actually played around with an idea that I called Cardassian cosmology, where I suggested that the equations should be modified. And these evolution equations for the universe that I talked about would have an extra term in the equation. And that extra term would contain matter and energy only, okay? But it would have a bizarre, powerful effect at these late times in the universe, causing the universe now to accelerate. So, and the reason I called it Cardassian cosmology is because that comes from Star Trek. The Cardassians are, I don't know if you watch Star Trek or not, but Cardassians are a bizarre type of species. They look like humans, but they're not, you know? So they're really weird looking, but in the end, they are made of ordinary matter, the ordinary stuff, just like we are, and their goal is accelerated expansion of their evil empire. So anyway, so that kind of idea that the equations need to be modified, I did that back in 2002. Yeah, my student couldn't even get a postdoc after writing that paper, but now it's very popular, that kind of idea that the equations are just wrong. So there are two possibilities when we talk about these three pieces to the universe, that the dark energy might not exist. It might be something else going on. And so, I don't know. It's hard to explain what's going on with the dark energy. It's a really unsolved problem, which means young people listening right now, please join the field. Help us figure this out. We need another Einstein.
Yeah. So I would like to ask you now, in what ways does an understanding of dark matter and dark energy might help us answer questions like what is the shape of the universe, or is that already something
Oh,
solved?
we know the shape of the universe. That was solved
Okay, okay, okay.
at the turn of the millennium by the microwave background measurements. So going backwards to Einstein's work, where then people applied it to the universe as a whole, they realized there were three possible shapes for the universe. We could be sitting on the surface of a higher dimensional sphere, which have a weird geometry. I mean, if you shot off parallel lines, then they would go around this sphere and they would bite you again from behind. Or it could have been a saddle geometry, and then parallel lines, wouldn't stay parallel, they would diverge. Okay, that's another weird geometry. And the third possibility is what we call a flat geometry. It doesn't mean two-dimensional, just means it's the same mathematics we learned when we were 13 years old. So no curvature to the universe. And so these three different possible shapes for this universe, the saddle, the sphere, or the flat, well, we know the answer, and the answer is flat. So the universe as a whole has no curvature. And the way we know this is because if you look again at these hot and cold spots in the microwave background, and then what you expect, the average size of one of those hot spots or cold spots, if the lines do travel in, if light does travel in straight lines, the size of those hot spots should be 1 degree in angular scale. In other words, looking across with your telescope, that should be 1 degree. And guess what? Whoop! That giant peak, it's called the Doppler peak, exactly at 1 degree. So sure enough, the geometry of the universe is flat. So that's, when we say shape, that's what I would mean by that there's no curvature. So it's not a sphere, it's not a saddle, it's just, I don't know, take a cube and go out to infinity in all directions.
Right. And what about gravity? Do we already understand what gravity really is?
No, not at all.
Okay.
So I mentioned the 4 fundamental forces of nature. So for the other 3, we do have a microscopic understanding. So for example, we know that 2 electrons repel each other. Now, the way this happens is that they're exchanging a virtual particle. You know, remember I said there's particles popping in and out of existence? Well, 2 electrons passing each other give off these virtual particles that push each other away. And guess what that virtual particle is for electromagnetism? It is a photon. It's a particle of light. So an electron gives off a very short-lived particle of light which pushes away the other electron. So that's how electromagnetism works. And for the strong force that holds our nuclei together, you have quarks, which are the substructure for protons, that give off gluons. So the gluons are attractive and they pull the quarks together, and that's why we have protons in the first place. It holds things together. And the third force, the weak force that I talked about for weakly interacting particles or for radioactivity. Again, there's particles, these are W and Z particles, and then they go in between but for example, in between 2 WIMPs, you'd have these W's and Z's traveling. So we understand those 3 forces at a microscopic level, but gravity we don't. So when gravity is really weak, like the gravitational attraction between 2 humans, okay, we know how to describe that in terms of, again, a graviton. However, when you get into strong gravity, like the extreme being black holes, no, we don't understand it. So it's so weird. I mean, Isaac Newton took an apple and dropped it. The apple from the tree fell on the floor, and he came up with the very simple Newton's law of gravity, which is very action at a distance. Somehow the Earth was attracting the apple, and we still don't know any better than that. Isn't that bizarre? So yeah, again, it boils back to the same problem. We need quantum gravity. So if we could do that, if we had a fundamental understanding of gravity, we'd also be able to understand what happened in the early universe. We'd also understand the centers of black holes. So this is a very, very important research area, but a really tough one.
Mm-hmm. So perhaps just one last question / topic. Do we know what the future of the universe will be?
You know, that's always a dangerous game to play, but we play it. I've written papers on it. So, yes, because the universe is accelerating, that gives us a very sad answer. That means, so, let's back up to the three possible geometries, and I'll tell you the different things that could have happened. So if we were living on the surface of a sphere, this sphere would reach maximum extent, but then the gravity would pull it back together, and you'd have a big crunch. Okay, so you reach maximum extent and then end up in a big crunch, everything crunching together. But for the saddle or the flat geometry, and we live, as I said, in the flat geometry, the opposite happens. Things spread apart, and very sadly, you end up with a big chill. Unless something happens to make it turn around again, in which case you get an oscillating universe, which is also I've also written models for that. But anyway, so the thing is, if you have, so that's even without accelerating universe, but with an acceleration of the universe, that really drives you to the big chill, where things get farther and farther apart, darker and darker, colder and colder. Everything gets torn apart, except for black holes still remain. But and so then the other question is, what about the fate of life in the universe? Not just the shape of the, or not just what the distances between things. What about life in the universe? So Freeman Dyson wrote some of the first papers on this topic, and so the weird thing is that life actually dies a heat death, which is not what you would think. But the reason for that is, if there's any kind of life, and I don't mean humans, or maybe clouds of stuff that somehow exchanges information like a computer or whatever, who knows. But anything that you do, you have to have some kind of metabolism, so you have to heat up. And then you have to get rid of that heat. You have to cool back down. And so the problem is, and this problem wasn't so bad in the times of Freeman Dyson, there were ways around it, but now that we have dark energy, it's much more difficult. Because if you have a vacuum energy, this is going to be hard to explain, but there's a Hawking temperature associated with that. There's a heat that goes with dark energy. So you metabolize, and then eventually as the universe gets colder and colder, you're operating at the same temperature as this dark energy temperature. You can't cool off anymore, so you die a heat death. But so my collaborator Will Kinney and I, and so this is based on my Cardassian idea, or if you have a time, maybe the vacuum energy is not constant, maybe it changes in time. Okay, if it decreases in time, slowly but surely, then you have some life that could still exist, because then instead of running into this wall of this dark energy heat, then what you're competing with is something that's still cooling off. So you could still continue to cool off in this Cardassian cosmology or this time-changing vacuum energy. So we wrote a paper about this. We were interviewed for New Scientist. And the guy who wrote the article, Philip Ball, here's what he said. He said, Katherine Freese and Will Kinney may not look much like superheroes, but they may just have saved the fate of life in the universe. So my answer to him is, how do you know that we don't look like superheroes? Because this was an interview by email. So if I had a Wonder Woman cape right now, I'd put it on. Anyway, just kidding.
Yeah. Okay, so Dr. Freese, let's end the interview here. The book is again The Cosmic Cocktail, 3 parts dark matter. Would you like to mention any places on the internet where people can follow you or find your work?
Well, the book is a good place to start, and the book is not just about the science, but it's also a memoir. It tells my story, the story of my career in physics, and I realized it also tells, I guess my goal was to talk also about the fun of being a scientist, the collaborators that I got to work with, and playing around with ideas, and the fun we have as people and as creative individuals. And so I like to tell that story in my book. And so that's why I like the idea of people taking a look. The other thing is, in the field of dark matter, for some reason, there's a lot of women who are the principal people in some of these experiments, who made some of the seminal discoveries and so on. And so if you look in the book, you'll see pictures of a lot of women. I didn't even think about it until after I wrote the book. So I'm thinking, oh, good, maybe this will influence some young women to be more interested in going into physics. So that book is Princeton University Press, but you can get it on Amazon. The Cosmic Cocktail, 3 parts dark matter, and it's not expensive, and it's in paperback at this point. So that's a good place. You want to read my views about everything we've been talking about. I mean, you can also look me up. I have a Wikipedia page. I have, so you put my name into Google, you'll find some pages. But I think the best thing is take a look at this at this book, which is it's not very expensive. You can have it tomorrow probably. So
Okay, great. So I will be leaving a link to it in the description box of the interview. And Dr. Freese, thank you again for taking the time to come on the show. It's been a real pleasure to talk to you.
well, this was a wonderful interview. Thank you so much.
Hi guys, thank you for watching the interview until the end. If you like what I'm doing, please consider supporting the show. It's thanks to people like you that it keeps running. I will leave links in the description box to Patreon and PayPal. Any amount, even just $1 per month, would already be a great help. Otherwise, and if you like what I'm doing, please share the interview, leave a like, and hit the subscription button. This show is brought to you by Enlights, learning and development done differently. Check their website at enlights.com. I would also like to give a huge thank you to my main patrons and PayPal supporters, Karen Litska, Anne Blanchett, Parerga Larsen, Lau Guerrero, Francis Ford, Ernst Frederick Sunda, Ricardo Vladimiro, Craig Healy, Adam Kessel, Olaf Alex, Jonathan Wiesel, Jacob Klinkby, Matthew Whitting, Arnold Wolf, Tim Hollacy, Enrique Alenia, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Voss, Bo Weingard, Rebecca Newberger Goldstein, Dan Demetrio, Robert Windager, Rui Inácio, Arthur Coe, Zup, Marco Neves, Colin Holbrook, Susan Pinker, Bernardo Seixas, Pablo Santurbano, Simon Colombo, Jorge Espinha, Phil Kavanagh, Corey Clark, Mark Blythe, Roberto Inguanzo, Michael Stormir, Eric Neumann, Samuel Andreff, Tiago Nunes, Bernard Ugni, Alexander Dunbauer, Fergal Cusson, Evan Bodrenko, Al Herzog, Don Ross, Jonathan Librand, Oslan Bullitt, Nathan Nguyen, Stanton T, Samuel Correa, Eric Hines, Mark Smith, J.W., João Eira, Tom Hummel, David Sloan Wilson, Yacila Des Araújo, Eden Solon, Romain Roach, Dmitry Grigoriev, Diego Londoño Correa, Tom Roth, Yannick Punter, Adana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pavel Ostazewski, Nelek Bach, Catherine and Patrick Tobin, Al Ortiz, Guy Madison, Gary G. Hellman, João Linhares, Lida Cosmidi, Sam Afzal, Adrian Yegi, Nick Golden, Paulo Tolentino, João Barbosa, Jules Price, Edward Hall, Edin Bronner, Franca Bortolotti, Gabriel Pons Cortez, Ursula Litske, my producers Isar Webb, Jim Frank, Lucas Staffini, Keon Gilligan, Luís Caetano, Tom Vanegdam, Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardas France, and Thomas Trumbull, and my executive producers Michel Rugieski, Rosie, James Pratt, Matthew Lavender, Sergio Codriano, and Bogdan Kanivets. Thank you for all.